Wow. Thank you. This is not my usual introduction, but it was great. I'll take it any day. It's a lot better than somebody reading off a piece of paper. So anyway, thank you so much for coming. I'm very, very excited to be here. I wanted to give you a little bit of my own introduction about where I'm coming from, just to give you a sense of how I got into the field of memory and maybe give you a chance to look at it the way I see it. So I started off actually not thinking at all about studying memory. I actually went to graduate school in clinical psychology. And so I was testing people with brain damage. And what was interesting was no matter whether somebody was worried about Alzheimer's disease or whether somebody had had a stroke or whether somebody had attention deficit disorder or they were clinically depressed, the thing that brought them into the clinic was memory. It was overwhelmingly the most common complaint. And in my own research, what I was doing was I was recording electrical activity in the brain and then trying to relate electrical activity to people's emotions. But to manipulate people's emotions, what we would do is we would ask them to remember times from their lives. These could be sad times, these could be happy times. But what struck me was if somebody took a moment to really pause and reflect on the past, it changed the way they looked in the present. It changed the way they felt in the present. It transported their mood from happy to sad or sad to scared or scared to happy. It was just remarkable, the power of memory. And so when I was in graduate school, just as I was finishing up, there was a technology that was developing called functional magnetic resonance imaging. And this technology allowed us for the first time to really scan people's brains and see entire circuits of the brain come alive as people were trying to learn and memorize things. And later on, I had a chance to record electrical activity directly from the human brain. And when I say I, it's always a big team of people who are really doing a lot of the hard work. And this is an example of one diagram of brain activity that we've analyzed in some specific ways. And then very recently, we started to get such big data sets that to really understand them, we needed to use large-scale computer models or computational models that are similar to the kind of neural network models that power modern AI to really try to understand what might be going on in the brain and to take the brain from this biological complex organism to basically a computing device and try to understand how information is taken in and processed and used to guide our behavior. And then that finally led me to this book that I wrote. So the reason why I wanted to tell you all that is because there's going to be little bits and pieces of all of this stuff in the story I'm going to tell you today. And even though I might be showing a brain scan here or a recording of electrical activity there or a study of a patient here, it all adds up, I think, to a bigger story. And the bigger story is the story of memory. So I actually grew up playing memory games. I didn't realize actually that the memory game that I would play a lot when I was a child was called Husker Du. It turns out it's a Danish game I discovered later. I actually learned first about the punk rock band Husker Du, which named itself after this game. And that turns out still to be one of my favorite bands of all time, as it turns out, which of course means do you remember, right? But I think I certainly feel, and I suspect many of you might feel this way too, that I don't remember the way I used to, right? When I first saw this meme on the internet, I thought, boy, this describes me to a T. I can tell you about every lyric of every bad song that I used to listen to in the 80s, but I cannot for the life of me remember why it is that I'm in the kitchen right now. And that's why I end up eating so much, because I'll walk into the kitchen and forget the fact that I came in there to look for my cell phone, not to grab food from the fridge. So this illustrates a major point about memory, which is we're usually aware of it when it fails us, right? And everybody I talk to, when I tell them I study memory, the first thing people say is, why am I so forgetful? Now, every once in a while, you'll see somebody who says, you should study me, I remember everything. And that's when I say to myself, this is probably the person who doesn't remember all the things that they're forgetting. So I think for the rest of us, we're all quite aware of our failings when it comes to memory, right? Now, what I'm showing you here is a graph. I'm going to show you a few graphs and figures, but hopefully I'll be able to make sense of them for you here. And this is a graph that shows data from the very first scientific studies of memory done by a scientist named Hermann Ebbinghaus. What Ebbinghaus did was he created a bunch of meaningless information for himself. He tried his best to memorize it, and then later on he would see how much of it he could retain over different periods of time. And what we get from this is something called a forgetting curve. So as you can see in that plot, the forgetting curve starts off high and it goes low. What that means is initially people remember a lot of the stuff that they try to memorize, but later on it goes down and down and down. And what strikes you about this graph is how quickly it goes down. So within 20 minutes of memorizing something to the best of his abilities, he had lost 40% of what he had tried to memorize. Within a little over 8 hours, he had lost almost 2/3 of what he had tried to memorize. So take this in your mind for a moment. The overwhelming majority of what you experience in life, at least the details, not necessarily the main bits, but the details, overwhelming majority will be lost in less than 12 hours, right? So if after 1 hour of my talking to you goes by, if you remember more than 15 minutes of this in a week from now, I will feel like this was a huge success, right? But it's really quite striking because we expect that we should remember everything. But in fact, what this data shows is that forgetting is the norm. We can expect that we will forget. And it's really, the question we should be asking is not why do we forget, but why do we remember anything at all? And that's part of why I titled my book, Why We Remember, because it's both a very specific question of why do we remember anything at all, and then a bigger question of, well, what's the purpose of memory? If we're going to be forgetting so much, why do we have the ability to remember anything in the first place, right? It would be like if we have the ability to breathe, but it's not like we're failing to breathe most of the time. And at the same time, we have this ability to remember, and yet most of the time we're not remembering. So in this talk, I'm going to give you an act in 3 parts. Part 1 is going to be getting into a very broad explanation of just in general why we forget, right? Then the second thing I'm going to get into is some of the basic mechanisms of memory, both that scientists have generally uncovered and some of the work that we've done in my own lab. And then I'm going to actually give you a little bit of data to hopefully convince you that we not only know how we remember, but we have some really compelling evidence as to why we have this capability in the first place, right? So let's go ahead and get started. Get your cocktails together for this. So let's talk about why we forget now, right? So in general, in neuroscience, we think that memories are stored through coalitions of neurons, right? And neurons are the basic cells in your brain that allow you to process information. When you have any kind of a conscious experience of seeing things, thinking, moving, that's neurons doing their job, right? So if you were to walk down the street, you met me, we said hi for some reason, I introduced myself, I said, hi, my name is Charan. Well, you would have some neurons that are active in your brain that would be processing the sights and the sounds, the smells, the sense of where you are. Now, in and of itself, the activity of those neurons gives you the conscious experience in the moment. But in theory, if we could reactivate those exact neurons in the exact sequence of events that happened previously, you could literally repeat that entire conscious experience. And that would be a full-blown recollection that would be so vivid it would almost be like a hallucination. But of course, that never happens, right? But what does happen is that we often get little bits and pieces of those experiences. And that's because learning leads to changes in the way neurons communicate with each other. Now, what I'm showing up there is a cartoon of two neurons that are basically talking to each other, so to speak, in the sense that one is projecting to the other and they can communicate chemically with each other. And during learning, what molecular neuroscientists have shown is that there are changes in the ability of these neurons to communicate with each other, so that the neurons that are active when you have a particular conscious experience will be more likely to communicate with each other more easily the next time around. And so what that means is that when you meet me, you might have a bunch of neurons that are active, and we can show in a cartoon like this a set of neurons that are more likely to talk to each other next time around, right? So in theory, you could see me again, and let's say one or two of those neurons would respond to my face, and then because they're this coalition, they will all come alive and allow you to remember my name. Now, that would be great, but life presents problems for us. And the biggest problem is we have lots and lots of similar experiences, right? Think of the things that you fail to remember most commonly: where you put your keys, people's names, where you parked your car. These are problems because we have so many repetitive experiences in our life. You meet many people with similar faces who have similar names. You put your keys in many, many places over the course of your lifetime. And that leads to a lot of very similar memories. It leads to a lot of clutter, right? And the problem is that memories can compete with each other. So let's take our example that I'm showing you before. So let's say after you meet me, you run into this guy, okay? And you could be forgiven because he kind of looks like me. And in fact, we get confused all the time. It's kind of a problem, but I'll take it, right? And so because we have these similarities, this person's face might activate some of the same neurons that were active when you met me, right? Because they're similar conscious experiences. And that's going to lead to a new cell assembly that has some of the same elements as the coalition of neurons that was keeping the memory for me, right? So then let's say later on, you go to a club, maybe a new Science and Cocktails, maybe you come back next year and you see this guy getting on stage, right? Well, now this person's face might activate a whole set of neurons. And the question is, can you tell just from the activation of those neurons whether it's me or whether it's that other guy, right? Because there's so much similarity in those coalitions, your brain can't tell which one is which. And so this is the problem that we struggle with all the time. It's why we can't remember where we put our keys. It's why we can't remember people's names, because we have so many of these experiences and we have this limited pool of neurons in our brain to work with to try to sort through all these experiences, right? So again, the question you could ask is, how do we manage to remember everything? And to get into that a little bit, I want to show you an example of somebody who's in the opposite end of the spectrum. Although really, they're a great example of how memory should work. And this is LeBron James. So for those of you who are not necessarily into sports, he's a professional basketball player. He's thought to be one of the greatest NBA players of all time. But what I'm showing you here is not just a description of his basketball, but actually a depiction of his memory. LeBron is legendary for being able to recall moments from his basketball game in extraordinary detail. And so what I'm going to show you here is a video of him describing one of the games he played in, and it's going to be showed in time synced up with the actual video of the game, okay? Okay, so how is it he's not only one of the greatest basketball players of all time, but he also has such an extraordinary memory? And I can't even figure out why I'm in the kitchen, right? What's up with that? But it turns out this example is not an example of photographic memory. It's not even an example of extraordinary memory. It is an example of intelligence and motivation and expertise. And this gets into the next question, which is, how do we remember? How do we succeed? Why do we succeed, right? And part of the reason why we succeed is we have two different kinds of memory. And of course, scientists like to dissect things, and in fact, in reality, everything's kind of entangled. But it's useful to think about memory as having these two different kinds of components. One is a component called semantic memory. And this is the knowledge about the content of events, right? So if you remember an event, well, you might remember who was in the event. You might remember what was in the event. You might recall where it happened, and you might remember why it happened, right? Now, all of those components are the building blocks, or the pieces of an event, right? Now, to someone like LeBron James, he has played in and he has seen so many basketball games, and he's studied the game to such an extent that, a play that might unfold in a rapid succession over time, he can look at this and assign it to one building block, one pattern that he has seen, and be able to reduce this mammoth complexity into the important stuff and distill the essence of it, right? And this is something that all of us have. So I like to say that memories, in some sense, are constructed in the way that you might play with Legos. You can take Legos, which are pieces, and put them together in particular ways to generate different structures. And likewise, you can take pieces of your knowledge about people, your knowledge about places, your knowledge about situation, and put them together to build a model of an event. And in fact, people in my lab, like my former postdoc, Zach Ray, has done great research to show that we reuse our mental representations of different people, places, and things. That is, that you can find maps of the brain that tell us information about who was in an event. And we can read out from the pattern of brain activity whether or not somebody is remembering person A or person B. And this network that we've been studying is called the default mode network. It's kind of a weird name. You might have heard of it. It's often misdescribed as this network of brain areas that's really involved in daydreaming or goofing off or hallucinating or whatever. But in fact, it's a network of areas that allows us to create these internal models of events, right? And when I say a model, I mean it very much like Legos. So this is an example of a Lego kit that apparently can be used to create these 9 different scenarios, right? Now, if we had to create a unique memory for everything we've ever experienced, that would be really hard. It would be a lot of work. But if we can take elements of our previous experiences and reuse them, that makes it a lot easier because we don't have to create something from scratch. We can take all the building blocks we already have and put together new events. And in fact, if you look at many of the events that we experience in life, they are so similar to other events that we can reuse the same components. So in fact, this is actually well known even in literary theory. There's a literary theorist named Joseph Campbell who argued, and I don't want to get into the details of this because I'm sure there's a lot of cultural misinterpretations and so forth, but what he argued is that every story has kind of a every culture has a universal myth. And we can see this played out, for instance, in many different kinds of Hollywood films like The Lion King, Star Wars, The Hobbit, Sleeping Beauty. All of these movies have this very characteristic structure that involves many of the same kinds of people in the same kinds of situations, doing the same kinds of things for this grand outcome. Now, what makes each of these movies different and compelling to us is the fact that they each have different content. But what makes them easily comprehensible, that you can sit in 2 hours and go from a long, long time ago in a galaxy far, far away to the Death Star being blown up, is the fact that you have this knowledge about the structure of events already in your head, right? Now, that's all fine, but we have a second component that we need to think about, which is, well, okay, but if I reuse the elements of events over and over again, I have a problem because every event is unique, right? This gets us back to the old problem of interference. That is, when memories are similar, they're going to compete with each other, right? And so we need to have some kind of a blueprint that allows us to say, well, these are the pieces to put together to be able to assemble this event. And these are the pieces we need to put together to assemble this other event, right? And so that is, in effect, episodic memory. Episodic memory is the ability to remember an event that happened at a particular place and a particular time just once. And that's what we would call the context. It's not about the content, but it's really about the fact that it all happened in that singular moment, right? Now, the psychologist Endel Tulving, who came up with the term episodic memory, he actually described it as something called mental time travel. Now, when I first heard this term, I thought, okay, this guy's kind of crazy. It's not very sciencey to talk about time travel, let alone mental time travel. But I realized later on, well, I was the one who was dumb because I just didn't have the vision to see it. Because in fact, I guarantee you, almost all of you have experienced mental time travel at one point or another, right? So think about it. I'm not going to ask you to actually say it out loud, but think about this. Have you ever heard a song, and this song brought you back to a pivotal time in your life, a pivotal moment, where it's not just that you remember that you've heard the song, but it makes you feel like you've been transported back in time? So for instance, for me, hearing the Dark Side of the Moon album by Pink Floyd is something that brings me back to a point when I was in college and I had gone out on my first date with a person who ended up becoming my wife, Nicole. And we had a very special first date at this Pink Floyd laser show. There were a lot of interesting smells in the audience and so forth. It was a very memorable event, right? And so in keeping with the music, science, and cocktails theme, this is a picture of a carajillo, which is a cocktail that I first tried actually very recently during a trip to Mexico. And I guarantee you, if I have that cocktail again, maybe at a future Science and Cocktails event, I will be able to taste my way back to Mexico, because that's a cocktail that tasted like nothing I've ever had before, right? So you could probably project this into your own lives. Songs, being at a particular place like your childhood school, or food that your grandmother used to make for you when you were a child. These are things that don't just bring up content, they bring you back to a mental context, right? So how does this happen in the brain? Well, one of the things that neuroscientists are starting to converge on is the idea that the brain state is never constant. If you're feeling bored, if you're feeling, excited, your brain state is still moving. It's always changing. And so one way we can look at this is actually, you're the first public audience to see this visualization. I literally had it generated just for this show. So if nothing else, remember that I've done this for you. And when I say I've done this, again, I didn't do this. This is actually a postdoc in my lab, Shuhao Shao, who generated this. And what we did was we took the hippocampus, which is a brain area that's essential for episodic memory. People who have damage to the hippocampus will show problems with episodic memory. And so what we did was we tracked brain activity using functional magnetic resonance imaging, or fMRI, and we tracked activity over time as people were just watching events unfold in a movie. And then what we can do is we can say, what if we can visualize the changes and patterns of activity, the flow of activity in the hippocampus over time? And what we find is that in fact, it moves in a flowing way over time. And so this is a way of visualizing this in 3 dimensions. It actually takes about 8 dimensions to characterize a lot of the movement of brain activity in the hippocampus. But that in and of itself is actually a very small amount. And, if nothing else, this is a very cool visualization. But hopefully you can appreciate from this that the fact that on the one hand, it's not jumping around randomly, but on the other hand, it's not standing still either. There's a lot of flow and movement, right? And that flow gives us a unique fingerprint for every moment in time that we experience. That is, this moment in time to 1 hour from now, our brain states will be different. And if there's a different fingerprint in the hippocampus, that allows us to put a different memory for what's happening now to something that happens 1 hour from now, okay? And in fact, what we've shown and other labs have shown, and this is a picture cutting through the brain, and that glowing blob is a set of areas within the hippocampus, where we found that those brain activity changes over time predicts people's ability to not only remember what happened, but to remember when an event took place, to be able to pull themselves back to the temporal context. So I've talked to you about semantic memory, and I talked about episodic memory. And I talked to you about LeBron James, who seems to have a great memory, right? Well, how can we put all these together to beat forgetting? Well, let's go back to your example of who these 2 people are that you've met, right? You've got these overlapping coalitions of neurons, but maybe you could do a little bit more work and put episodic and semantic memory to work to be able to do a better job of disentangling these memories, right? So my name is Charan. This guy, as it turns out, is a movie actor named Charan. So you can say, okay, well, you meet this other guy. He's got this other part in front of his name that's very different, right? I'm a scientist who dabbles in music on the side. He's an Indian film superstar. So right there, there's kind of a difference between the two. He's probably playing even bigger audiences than this one as we speak, right? And finally, you can remember the context, which is that you might remember me from this event, which is about my book, Why We Remember. And you might remember him if you've been into Indian films. He was in a film called RRR, right? So once you kind of figure out what's distinctive about meeting me and what's meeting him, now you can get these very distinctive memories that show up that are not going to overlap as much. They're not going to be competing with each other, okay? And so if you can put meaning to work to be able to figure out how to organize information, you can take a LeBron James approach to being able to take this massive complexity around you and simplify it, but also to take stuff that's happening and simplify it into building blocks that you already have. And likewise, if you focus on the context, you can take note of the particular details that make this moment different than every other moment that you've experienced, right? And I can't help it, but I have to say that we live in an age right now where people talk a lot about intelligence. And frankly, there's a lot of stupid things that are being said about intelligence, right? So for instance, nowhere do you see more stupid things being said about intelligence than in the world of artificial intelligence. This is just an example, and I don't mean to pick on him. He's certainly far wealthier than I am, and certainly much better at certain things than I am. This is Sam Altman. And Sam Altman runs the company OpenAI that produced ChatGPT, which many of you might know. And so he and others in the field have been talking about this phenomenon called artificial general intelligence, and the idea that computers will soon be smarter than people. And he even threw his child under the bus, and he said, I didn't think his child was even born at the time, and he had said, my child will never be smarter than AI, right? And to which I wrote a reply that was read by far fewer people saying, no, there's no comparison between human intelligence and machine intelligence, right? All of these problems that I talked about with memory competition, they're gigantic problems in AI. To train a model like ChatGPT, it takes gobs and gobs and gobs of data. The amount of energy used by ChatGPT could take down an entire power grid, right? Now, on the other hand, each of you, as brilliant as you are, your brains are using less power than any one of these light bulbs up here. That is the difference between people and machine. And part of why we can do this is because we're doing so much less. We have semantic memory to really reduce the complexity of information in our world, but we have episodic memory to help us be nimble and quickly learn the little bits and pieces that make this piece of information unique, right? So in other words, if you have a favorite restaurant that you like to go to, and one day you show up at the restaurant and the menu is completely changed and you see a sign that says under new management and the food is terrible, now you have one experience that you can learn from and you don't have to ever go back to that restaurant again. But if you're ChatGPT, you need a lot more experience with that restaurant to figure this out because you have to overcome all of the examples of good food that you had there, right? And so semantic and episodic memory allow us to be really smart because we can take advantage of the general way things work in the world, but we can also stop on the dime and learn the exceptions to the rules very quickly. And this gets me into the third part of my talk, which is where we get into the most data, which is the question of why we remember in the first place, right? So we tend to think memory should be a comprehensive repository of our past, right? But that's not really how it works, right? And the analogy I like to give is when you're packing for a trip, because I have to travel quite a bit. So for instance, last night, I was nervous about this talk. You might tell because I'm walking around all over the place. But I was nervous. I woke up in the middle of the night, and I eventually went back to sleep. Now, if I did not have episodic memory, though, it would have been different. Let me explain that in just a second. But The fact is that memory was allowing me when I woke up to ground myself because I could use the past to make sense of where I was in the moment. I could use the past to understand why I'm in this hotel room right now. I could use it to remember where I am. And I could use memory to think about why I'm awake in the middle of the night. It's because of what I have to do the next day. And thinking about this talk, and actually I was making some notes about things that I should say in this talk when I woke up, right? And so memory allowed me to do that. Now, when I used to work in the clinic, one of the things that I noticed was how disturbed that sense was in people with memory disorders. So many of you might have a relative with a memory disorders. Alzheimer's is very, very common, unfortunately, tragically right now. And one of the things that makes Alzheimer's scary is people feel like they are lost in space and time. This is actually a kind of a cool segue to an experiment which really brought this home to me, which was an experiment that I did as the only research I've ever gotten involved with that involved sea lions. So what I'm showing in this picture is a picture of what's called a red tide, which are unfortunately phenomena that are becoming extremely common these days. And a red tide is a phenomenon where there's a big algae bloom, and these algae produce a toxin called domoic acid. So when these algae pop up, they produce this toxin, and fish will eat the algae. Now, certain feeders like sea lions will eat those fish, and sometimes they'll binge on those fish that are binging on this bloom of algae, right? And the toxins can accumulate and cause brain damage. And so what happens is these sea lions end up washing up on the California shore. And so what I'm showing you here is a picture of one of these sea lions that was rescued, and a guy named Peter Cook, who at the time I met him was a graduate student. And Peter was working and doing research on these sea lions that were being rescued, and he was trying to understand what was leading them to get washed up on shore in the first place. So I saw him give a talk, and my first thought was, I have to meet him so that my daughter can meet a sea lion. and we did get to do that, and he was doing such amazing research that I ended up on his dissertation committee, and then we collaborated. And we did one of the coolest experiments ever, which is we started to do memory experiments on a sea lion, on these sea lions. And what we found was that this domoic acid toxin that was showing up in the algae, it turns out could cause damage to the hippocampus. And in fact, this actually happens in humans too. There's a phenomenon called amnestic shellfish poisoning that people can get if they eat too much shellfish or sushi that have been feeding on these kinds of algae. So in the case of sea lions, this domoic acid is highly toxic to the hippocampus. It's even used in research in rats where they try to study epilepsy. They use this toxin to actually damage the hippocampus. Well, what we found was if you gave animals a test of memory for where they are, right? We would put rewards in different parts of the tank that these sea lions were walking around in, and they could go, if they remember, they could go find those rewards. And what we found was that animals that had lower hippocampal volume, meaning that their hippocampus was kind of shriveled up, performed much more poorly on this test. So what this is showing here is what's called a scatter plot. So on the y-axis is how long it would take them to find actually I think this was errors, the number of errors they were making in trying to find the food. And on the x-axis is the volume of the hippocampus. And what you can see is that the animals that had very low hippocampal volume were very poor at this task. And then what we did was what I believe is the first functional MRI study that was ever done on the sea lion. And this is kind of why I like to show this, because it's just so cool that we got to do this. So we scanned the sea lion's brains, and we looked at activity in different brain areas, and we asked, how is the brain functioning as a whole? And what we found was these areas in the default network that I was showing you, that semantic memory network, many of these areas were showing these correlated fluctuations in activity. And in a sea lion that had a normal hippocampus, they were correlating quite well with the hippocampus. And this is what's shown here with those little orange lines between those dots. That means essentially that you have areas of the brain that are talking to each other and working very closely together. Now, in the animals with domoic acid poisoning, what you can see is these blue lines, which basically means these areas are not talking to each other very coherently. They might be talking, but they're not hearing each other, right? And so we now had a reason to explain why these sea lions were washing up. These sea lions were getting damage to the hippocampus because we were degrading the environment. And then, as a result, they were disoriented. They were lost. Well, if you're a hunter, you're a forager, you need to know where you are in order to eat. So these animals are starving. They're having seizures because of the hippocampal damage, and they don't know where they are, and they end up lost and washing up on the shore. And so we were able to trace what was happening in the environment to what was happening in the brain, to what was happening psychologically, to what was happening then with them, the outcome of them being washed up on shore. And again, take a moment to think about this, because for me, waking up in the hotel, if I didn't have a hippocampus, I wouldn't know, am I here because of a vacation? Am I in this hotel because of a business trip? Or I'm in this hotel because I got kidnapped? I would not know if I did not have a hippocampus. I would be existentially floating in space and time, just like some of these sea lions. So memory plays a big role in orienting us and grounding us in space and time. But that's just the present. We can also think about the role that memory plays in the future. So I mentioned this idea that many of us might show up in the kitchen and not know why we're in the kitchen, right? And that's a consequence of something called event boundaries. So to illustrate that, I'm going to show you a cartoon. I know many of you are probably too young to remember this cartoon. In the US, we call it peanuts. I think here it's called turnips. I'm not sure. But in any case, what I'm going to show you is a comic strip. And this comic strip is going to illustrate a very typical sequence of events. So in this comic strip, there's a character named Charlie Brown. There's a girl named Lucy. Lucy is holding a football. Now, I know this isn't football as we call it here in Europe, but just imagine it's a similar kind of concept. She's holding a football, and if you understand the game, you can realize that Charlie Brown is looking, and even though you're not seeing it, you can probably guess that he's thinking about kicking the football. And so it's entirely predictable that he's going to walk away from the football because he's going to run up to kick it, right? And so, in fact, it's quite predictable that he is running up because that's what you do if you want to kick a football. But typically, this does not happen. Typically, you won't have a person pulling away the football and then Charlie Brown's flying. And now your understanding of the event is completely different. You're no longer thinking about whether or not he's going to kick the ball very far away. You're thinking about whether or not he's going to get a concussion, right? And so your whole understanding of the event has changed. And so that's what we would call an event boundary, that moment where your understanding of what's going on has changed, right? Now, if memory works properly, you should be able to use information at event boundaries to make better predictions the next time around. So for many of you, if you happen to have read this cartoon many, many times, as older people in the US have, you'd actually be very familiar with this, and you'd know as soon as you see Charlie Brown and a football and Lucy, that this is exactly what's going to happen, right? And that's a big purpose of memory, to take this scary, uncertain future that we have in front of us and make it routine, to make it predictable and dull. So with event boundaries, what happens is we don't just have this continuous flow of brain activity over time. In fact, our mental context shifts quite abruptly. And that's what makes it hard to travel back in time when you've gone into another room, say. Now, to study event boundaries in our own lab, we've had to create movies, we've had to create short stories. People in my lab have become artists. This is actually a great one. This is an animated film that was created by a postdoc in my lab named Alex Barnett. The character, by the way, here uncoincidentally looks a little bit like Alex. So I'll just show you a small clip from this.
Ours will only grow stronger. You should know this better than anyone. I know the stories they say about you. What happened at Fair Falls?
Enough. Now, do you have a plan or not?
First, I need Hector. Let me ask you, do you trust your brother?
With my life.
With your daughter's life?
Yeah.
You must speak with him tonight.
Okay, so that's just a tiny clip, but my suspicion is that your mental context changed at least twice during that clip. Once, when he says, with your daughter's life, because now all of a sudden she has to think about things a little differently, and you're now changing your predictions about what she's likely to say. And the other would be later that night, because there now there's a big change in time, there's a big shift in place and so forth. And so we tend to have these event boundaries in our own lives at similar kinds of moments, when there's a change in a conversation topic, when we move into another room, or when something happens to us, right? So it turns out that when people watch movies, we're very good at detecting event boundaries. All you have to do is show someone a movie and say, push a button when you think one event has ended and another is about to begin. Now, this is a very open-ended instruction, but what I'm showing you here is a plot of many people. There's 28 people who watched Alex's movie. And the height of each bar shows the number of times somebody pushed a button at that point in time. And what you can see is there's a little bit of variability, but on average, many people agree at certain points there is an event boundary, right? So there's a couple of points where all 28 people agree. And there's a certain set of points where, in fact, at least over half to 2/3 of the subjects agree that there is an event boundary. Now, these are people who we got data from who were watching the film, but we didn't get any brain activity from them. We took a separate set of people and we scanned their brains, and what I'll show you is brain activity from one area of the brain that's part of the default network. And what you can see here is the brain activity measured with MRI spikes almost perfectly at those moments when other people would say, yeah, an event boundary is taking place here. So this is a map of many areas of the brain. It's not every area of the brain that shows this effect, but there's a certain set of areas in the brain that characteristically activate during event boundaries, and these are areas in the default network and in the hippocampus that is using semantic and episodic memory at these moments. As it turns out, one of the most surprising findings that we've gotten in our lab, and other labs have gotten too, is that when you have events that have these kind of predictable structures to them, like what you see in movies or what you see in stories, the hippocampus is not continuously encoding memories. It turns out there's a little spike in activity in the hippocampus at these event boundaries. And so here what you can see is a little red line that I've artificially put in between two scenes in the movie. And a little spike in activity in the hippocampus during that red line can predict whether or not somebody will remember the entire 20 seconds that came right before it. It's that remarkable. Now, my former postdoc, Zach Ray, did a study looking at a data set of 546 people watching a movie. And we again looked to see what was happening at event boundaries. And these people ranged in age from 18 all the way up to the 80s. And what we found was in the hippocampus, on average, we see activity all over the place. So what's shown up there is a change in MRI signal, which is related to brain activity, time locked to when an event boundary takes place. And you can see right before people would generally say, here's an event boundary, there's a little increase in activity that takes place, right? But older people, which is the curve shown in green, show less activity at event boundaries than the younger people do. And middle-aged people are somewhere in between, right? But there's a lot of variability amongst young, middle, and older people. And so we started to ask the question, well, what does this all mean? Well, maybe if hippocampal activity is relating to the ability to encode memories, maybe people who have less event boundary activation also have poorer memory performance. Well, so we looked at data from this huge number of subjects where people were doing a test of memory for stories. And this is completely different from anything that they were doing in the MRI scanner. They get tested 2 hours later. We can see how well people can retain these stories over time. And what we found was a mammoth correlation between brain activity that people had in the scanner during an event boundary and people's ability to remember these stories outside of the MRI scanner. In other words, what we had was a marker that we could use to point to individual people and say, how good is your ability to remember events? Just from these moments in time that were event boundaries. If you looked at non-event boundaries, you don't see this beautiful effect, right? What's really amazing is, even if you remove the effect from age, statistically speaking, people who showed more event boundary activation would show better memory, which means that it explains a lot of why some people tend to be very poor at remembering things when they're older, and other people are older and they're actually remembering things very well. So we're taking this method now, and we don't have any data on this yet, but we're collaborating with one group in Germany to look at people who might be at risk for Alzheimer's disease to see if we can use this as a marker, a biomarker of memory. And we're looking at another group of people who have been studied in Chicago who are so-called superagers. And so these are people who, at the age of 80, show the memory performance of a 50-year-old. And so we're hoping we might be able to find these markers that we can use to be able to track people's memory performance in a way that could identify whether or not they might be at risk for a memory disorder. So more on that, hopefully in the next Science and Cocktails, not too long from now. But these are movies and stories, but they reflect things that happen in real life. As I mentioned, entering a room can make you feel like there's an event boundary that's happened, right? A change in conversation topic can make you feel like there's an event boundary. How many of you have been in a conversation, somebody picks up their phone all of a sudden, and then they come back, and then you're like, what were we talking about again? Has this ever happened to you? I find this happens to me a lot. Aging is hard. What can I say? Sometimes when we end an activity, like you're doing the dishes and you stop and you move on to something else, you experience a mental event boundary. And a big one is surprise. Surprises are very big in terms of creating event boundaries for us. And this brings me to kind of my last big point. Well, my second to last big point, which is that event boundaries help us prepare for the future, right? So I realize I've been blasting you with a lot of media, but I'll give you this as another example. This is from a study with my collaborators from Yuval Neer's lab. And I'm going to show you a little video. Just watch it. It's kind of fun. It's not too long.
Whoa. We got a big issue, bro. You want to know what our issue is?
What?
You about to get jumped, Holmes.
All right.
You about to get jumped. You ever been jumped before? Well, you about to get jumped, bro. Ow!
Okay, if you're not from America, that might seem very puzzling. This doesn't happen actually even much in the US, but people do talk like that if you hang out in basketball courts. But that was a very surprising thing, right? But if you knew this guy, theoretically, this would be a very informative piece of information that he likes to play practical jokes. And this would be like something that you'd want to remember. But memory, if you think about it as being about the past, it's something you can look back and consciously say, wait, did that happen? Oh, I remember when this blah, blah, blah. But that's not really how memory works in the moment. What I'm going to show you here is the same video, but no sound. But what we're going to do is we're going to look at the eye movements of one person. The blue is going to be the first time they watch this video. And that circle over there is going to tell you where the person was looking, okay? The green is where the person was looking the second time that they were watching the video. Now, I'm going to spoil it a little bit for you because it goes by kind of fast. But basically, there's not a whole lot to look at in this video for most of it, except for the two guys who are standing together talking, right? And so you can expect if somebody's paying attention to what happens in the moment, their eyes, those circles, should be locked onto the people who are talking. But if you have memory, you can make a prediction before something happens. You can look for that dinosaur before it actually runs out, right? So let's see what this person does. Look at the blue dot for when they're naive, and the green dot when they can actually predict. So what you could hopefully see there is when a person's naive, they're looking at what's in front of them, and they're even kind of slow on the take when this thing happens. But the person who has memory, they're not asked to remember anything. They're not asked to look at what's about to happen. It just happens. People look where the event is about to take place, and memory is coming to the rescue to allow them to do that. So one of the really interesting findings from this study is that, in fact, we tend to think that our memories fade over time, that is, they actually get worse over time. But it turns out that sometimes you can get improvements in memory, and one of those improvements, it turns out, is related to this predictive functioning. So Yuval's group basically measured how good people are at predicting what's about to happen. Are they doing a better job at looking where the surprising event is about to take place? And they looked before and after sleep. And sleep is really interesting because even though sleep feels like a waste of time for many of us, in fact, even in my daily life, I feel like it's a waste of time, even though I know better. I'm friends with Matt Walker, who wrote Why We Sleep, and so I really should know better. But it feels like a waste of time, but our brains are doing stuff when we sleep constantly. There's a whole symphony of waves that are happening in the brain. In the neocortex, in these areas of the default mode network, there are these slow waves that you see in these little bumps called sleep spindles. And in the hippocampus, there's these little bursts of activity taking place when there's packets of information being transferred from the hippocampus to the default mode network. It's this moment in time where your brain can take all of the events that you've experienced, all of these episodic memories, and consolidate it to update your knowledge base, to build better semantic memories, and to get the system to work better together. And it turns out that people are actually better at making these eye movement-based predictions after they've had a night of sleep, relative to if you wait the same amount of time and you're just awake, right? So again, I want you to take, as a memory researcher, I find this startling because memory never gets better over time, at least subjectively speaking. It always seems the older a memory it is, the harder it is to remember it. But this is an effect of memory being used for the surface of prediction. And that's where the brain seems to be optimized. It's not optimized for saying, hey, what happened in the past? It's being optimized for using the past to predict the future. Now, in that study, they didn't measure hippocampal activity, but we've done a lot of work to measure activity in the hippocampus. And we've shown during different surprising experiences, there's bursts of brain activity in the hippocampus. This is a map that we've gotten with functional MRI data, where we scan people while they're watching different things, and sometimes there's surprises that take place. And what we find is that the burst of activity predicts people's ability to remember these things better. We actually also had an opportunity to look at patients who had electrodes implanted in the hippocampus. So these are patients who are being treated for epilepsy, and their seizures are so bad that the surgeon wants to know where the seizures are coming from so that they can surgically remove those parts of the brain that are causing the seizure. So you have these patients who are in the hospital for a few days, and they have electrodes in their brain, and we can then actually study them in simple memory experiments, just like we do for a person in an MRI scanner. But now we're getting electrophysiological moment-by-moment measures of activity in the brain. And so in these patients with electrodes in the hippocampus, we could see what happens in the brain when people are seeing things that are expected, when they're seeing things that are unexpected, right? Now, this is what's called a spectrogram. It's showing activity in different frequencies of the brain. And I know this is kind of it's a complicated picture, but here's the point that I want you to take note of, is that when people are seeing something that's fully predictable, there's a little burst of activity that's in low frequency that says, yeah, something's happening. Likewise, when there's something unpredictable, you see that low frequency activity, and that's that little red blurb that you see in both of those at the bottom. But what you can see is when there's something unexpected that's happening, there's these bursts of high frequency activity. This is called gamma activity. And this is basically the hippocampus saying, hey, something very important is happening at this moment. And you don't see those same bursts nearly as much when people are processing something that they expect. So in both the fMRI and the EEG data, what we're seeing is the hippocampus is highly responsive to the unexpected. Now, we don't know the cause and effect relationship, but this is not just happening in the hippocampus. This is actually a map of different areas of pathways in the brain that are involved in communicating via the neuromodulator dopamine. Now, just quick show of hands, how many of you have heard of dopamine before? Anything about it? Okay, good. So many of you probably have heard about dopamine in the context of reward or pleasure. Some people call it the pleasure chemical. And unfortunately, this is a little bit wrong. It's actually very wrong. But actually, what dopamine seems to be important for is at least two things. One is signaling that something important is taking place and energizing you to deal with it. And the other is driving plasticity. In all sorts of animal research, people have shown that when you manipulate dopamine activity, you can make the brain more plastic, able to form new memories easier, or you can reduce plasticity and make it harder to learn, right? So with MRI, we could identify very small areas of the brain. This little white area that you can see there at the base of the brain is called the ventral tegmental area. And so we could scan this with MRI, but it's very small and hard to measure. Now, it turns out we were able to also look at patients with electrodes implanted in a different area called the nucleus accumbens. And this area of the brain is part of this circuit that interacts with the VTA. It's highly involved in signaling salient information, whether it's rewards or whether it's surprises or what have you. And we could look with both electrical activity and functional MRI. And what we see with MRI is that, in fact, when there's unpredictable experiences that happen, we see activation in a healthy subject. And just like in the hippocampus, when we record from the accumbens, in this dopamine circuit, we see a massive blast of that high frequency activity when something unexpected is happening, right? So let me, I know I've told you a lot of information, but let me just backtrack here and simplify it a little bit. Not every moment is equal. A lot of our lives are fairly predictable and boring. But if we can really focus on those moments that are unpredictable, those are the moments that can provide us the most information. Those moments where we make errors in our prediction can provide us information. And just what I want to close up on is the idea that those moments are not only moments where your brain is plastic and you can learn about what's happening in the moment, but that can also stimulate us to do things, to explore, to be curious. And so this last bit is work that was entirely driven by a former postdoc in my lab named Matthias Gruber. And Matthias had done his graduate work at University College London, and so he would go to the pub quizzes, right? So he would sit and watch with fascination at people who sit in these pubs and just do trivia questions all night, right? And some of the appeal of trivia questions isn't just knowing everything. If you know that you will know the answer to every question, that's not nearly as exciting as the challenge of thinking you might know everything but not being sure, right? And occasionally getting stumped by a question that you think you should know. So for instance, I'm a rock music fan, and so before I did this experiment, if I had gotten a question like this, I would have been a little stumped because I would have said, well, I know there's a lot of Beatles songs that were hits on the chart. I don't know which one had spent the longest time in the chart, right? So this is the kind of question that would make a person like me curious. Now, any of you, if I were to ask, you might be curious about different things. You're clearly curious people, which is why you're interested in an event like Science and Cocktails, right? And that curiosity seems to be driven by a mismatch between what you think you know and what you actually are being exposed to at the moment. A question like this can create an error in your mind, a surprise, because it's exposing a gap in your knowledge. So to simulate this, what Matthias did was he created an experiment where he gave people a whole lot of trivia questions. And what we would do is we would rate the questions for how curious a person was to find an answer to a question, okay? So let's say you had a bunch of these trivia questions. Then there's a bunch that you don't know the answer to, and you're sitting in an MRI scanner. And imagine you're lying in an MRI scanner, you're looking at a little screen, and the screen's going to show you some stuff. The screen's going to show you a question, and then it'll eventually show you the answer. And so this is, imagine you're in this experiment, this is what it would look like. Okay, so pretty simple experiment. We did a lot of these trials in the MRI scanner. Sometimes people are very curious about the question, and sometimes people aren't curious about the question, right? So when we actually look at people's brain activity, what we find is that people's brain activity in this dopamine circuit is exquisitely related to how curious they are, right? Now, let me pause for a moment and say, so if dopamine, let's say, was this reward chemical. Rewards are things that you get. Let's say somebody gives you a cocktail and you might have a spike of dopamine, right? If it was truly a reward, that's what would happen. But a question that you don't know the answer to is not rewarding. but a question that you don't know the answer to, you might be curious enough to try to find the answer. And that's what the dopamine circuit seems to be doing, is it's energizing us. Whether it's energizing you to get a cocktail as soon as this event is over, or it's energizing you to kiss your partner, or whether it's energizing you to seek out more information to try to understand what the heck this guy was talking about tonight. All of those cases are cases where dopamine seems to be driving the bus here, right? So in this circuit, I'm showing you two different brain areas, and those lines show essentially how much activity that we have in the brain during moments when people are seeing a question that was either associated with low curiosity, like a 1, or high curiosity, which is a 6. And in both cases, you see this increase with more curiosity being associated with more activity. Now, we also saw that these circuits were interacting functionally with the hippocampus during these questions. And critically, that had two effects. One effect is it helped you remember the answers to the questions that you were curious about. So for instance, if you were curious, the answer to that Beatles question was, "Hey Jude," okay? Someone got it right. All right, good. I'll get you a cocktail after this is over. So anyway, unsurprisingly perhaps, people are more effective at remembering the answers to questions that they're curious about, those high curiosity questions, than they are at remembering answers to questions that they're not so curious about, the low curiosity ones. But what's really cool is nobody was curious about these faces that I show. All we asked was a dumb question of, do you think this person knows the answer? But it turned out that, in fact, when people were in this state of curiosity, that they were better able to remember the faces that came up right before the answer. In other words, giving a question to people that trigger their curiosity open this window plasticity and help them take in other information that came along for the ride, okay? So that was a very cool and unexpected finding, and that was associated with the synchrony between these dopamine processing circuits and the hippocampus to be able to give you this added boost in episodic memory. And Matthias has done more and more work, and what he's found is children show this effect. Elderly people show this effect. Everyone seems to benefit from curiosity. And so I think this is a very important thing, because I think we can all afford to be a little bit more curious, right? And curiosity is a great way to just enhance your natural memory performance. So I know I've told you a lot. Maybe you're feeling thirsty right now. Your first cocktail is wearing off. So let me just close up by giving you a summary of where we've gone here, because I know it's been a big journey. So number one, we have a lot of competition between different memories. It's amazing that we remember anything in the world, right? We can get around this competition or remember some things through this combination of semantic memory and episodic memory. But the key thing to keep in mind is none of this is about the past, because the past, by definition, is over. We live in the present. Every moment that you're thinking something is in the present. But you have this remembering self, a part of you that has access to the past. And that remembering self can allow you to make sense of what's happening in the moment. It can tell you where you are in space and time, and it can tell you why somebody is talking about the things that they're talking about in front of you. And it gives you a window into the future. It gives you the ability to take what's happening in the past, happened in the past, take what's happening now, to imagine all of these different possible worlds for yourself. And so rather than asking, why am I so forgetful? The question I really want you to ask yourself is, what are the memories that you want to carry into the future? Because if you're intentional about your experiences, you can use memory to actually make better decisions and to live better lives. So all of the work that I talked about was really the process of many, many scientists in my lab who've gone on to great things, many collaborators at different universities, as well as people in my lab right now. I've also included my wife, who's been very supportive to me as well. And, I want to say finally, it's hard to be a scientist right now because we hear a lot of anti-science rhetoric from a lot of people. So I just want to thank you so much for your curiosity in science, and thanks for putting up with me all this time. And I hope to answer some questions over the next few minutes. Thank you.